Now let's turn to the distinction between bound states and unbound states. The key points are given at the beginning of this page. For a time-independent self-adjoint Hamiltonian in standard Schrödinger problems, bound states are square-integrable energy eigenstates belonging to the discrete spectrum, whereas unbound states are described by non-square-integrable generalized eigenfunctions associated with the continuous spectrum. We begin with the simplest and most standard case, which is a time-independent Hamiltonian. In this case, a stationary bound state is a square-integrable energy eigenstate. In other words, it satisfies the time-independent Schrödinger equation as shown here, and at the same time the eigenfunction belongs to L squared, meaning that its norm squared is finite. So there are really two essential ingredients here. First, it must be an energy eigenstate. Second, it must be normalizable in the ordinary Hilbert space sense. When both of these are true, we call it a stationary bound state. Such states belong to the discrete spectrum. This is very important. In standard Schrödinger problems with a time-independent confining potential, bound states correspond to isolated allowed energies, E sub n, not a continuum of energies. That's why the bound state energies are said to be quantized. If we normalize the eigenstates, then they satisfy the orthonormality relation as shown. So these stationary bound states fit exactly into the discrete spectrum framework we developed earlier. Typical examples include the infinite potential well, the quantum harmonic oscillator, the finite square well for its bound levels, and the hydrogen atom for its negative energy discrete states. You may want to review or study these examples independently because we won't be able to cover them in detail here due to limited time in one semester. In all of these examples, the particle is spatially localized in the sense that the wave function is square integrable and can be normalized to 1. So the main message of this slide is this. For a time-independent Hamiltonian, a stationary bound state is a normalizable energy eigenstate belonging to the discrete spectrum. Now we move one step beyond the stationary bound state. A system can still be physically bound even if its state is not a single energy eigenstate. For a time-independent Hamiltonian, a general bound state may be a superposition of stationary bound states indexed by integers, as shown in this expression. This state need not be an energy eigenstate, and therefore it need not be stationary. In particular, probability densities or expectation values may vary with time. However, if all the basis states appearing in the superposition are bound eigenstates, then the entire state remains within the bound state subspace. Physically, the particle is still bound. This is an important point. Being bound doesn't necessarily mean being stationary. A stationary bound state is one special case. A superposition of stationary bound states can still describe a bound particle even though the state involves non-trivially in time. We then turn to the case of a time-dependent Hamiltonian. Here, the usual energy eigenstate definition of a bound state may fail because the Hamiltonian may not admit stationary states at all. For example, if the potential changes explicitly with time, then the usual separation of variables may no longer work, and there may be no meaningful time-independent energy eigenfunctions to use as a definition. In that more general setting, the idea of a bound state must be formulated in terms of spatial confinement of probability. That idea is mathematically expressed as shown in this expression. For every epsilon larger than 0, there exists a finite radius r such that the integral of the absolute square of time-dependent wave function over a region outside a ball of radius r is smaller than epsilon for all time. In words, that means we can choose a sufficiently large but finite region so that at every time, the total probability outside that region is arbitrarily small. That is a rigorous way of saying the particle remains confined. So for time-dependent Hamiltonians, the more robust definition of bound is not based on energy eigenstates, but on persistent spatial localization over time. Examples of systems with a time-dependent Hamiltonian include a particle in an infinite well with moving walls, a harmonic oscillator with a moving center or time-dependent frequency, and a hydrogen atom in a weak time-dependent electric field. In all of these cases, the Hamiltonian changes with time, so the notion of a stationary energy eigenstate is no longer the central defining feature. What matters instead is whether the probability remains confined. Let's now turn to unbound states, also called continuum states or scattering states. Unbound states are states corresponding to the particle's total energy eigenvalue larger than or equal to the potential energy as the distance from the origin goes to infinity, as shown in this inequality. The case where capital E equals V infinity corresponds to the threshold of the continuous spectrum, which is a special limiting case and may require special care, but conceptually it marks the onset of unbound behavior. Most potentials we study in quantum mechanics are short range or approach a constant value far away from the origin. Without loss of generality, we can always shift the potential so that the potential energy approaches zero at infinity. We now explain unbound states in more detail. An unbound state is not spatially confined. Physically, unbound states correspond to particles that can propagate to infinity, so the wave function extends through space. It doesn't decay fast enough to be square integrable, so it is generally not square integrable in the ordinary L-squared sense. In standard Schrödinger problems, unbound states are described by generalized eigenfunctions rather than ordinary normalizable wave functions. One standard example of generalized eigenfunctions is the momentum eigenfunctions, which are plane waves. Therefore, wave functions representing these states are not normalized to 1 in the usual way. Instead, they are delta function normalized, as we will review this part on the next slide. Note that unbound states are labeled by a continuous variable such as energy E, momentum P, or wave number K. A standard example is the free particle in one dimension, whose wave function takes the plane wave form as shown in this equation, and its energy is given here. Since K can vary continuously, the energy also varies continuously. Therefore, the spectrum is continuous rather than discrete. Notice that a single plane wave does not represent a physically realizable state. So the core idea of this slide is unbound states are continuum states, not spatially confined and not square integrable in the ordinary Hilbert space sense. Other common examples of unbound states include scattering states above the asymptotic level of a finite potential well, and scattering states in a finite potential barrier. Notice that in the potential barrier case, a state with an energy larger than 0 but below V0, which is the maximum potential energy within the system, can still be an unbound scattering state in which the particle is not confined and the wave function is oscillatory far away from the barrier, even though classically the barrier top exceeds the particle's total energy, capital E. So for ordinary scattering states, unbound states usually mean capital E larger than V infinity. In scattering problems, these are the states used to describe incoming, reflected, and transmitted waves. Now let's ask, if unbound states are not square integrable, in what sense are different unbound states orthogonal? The answer is that their orthogonality is expressed in the distributional sense using the Dirac delta function. If we label unbound states by the continuous energy, capital E, then the orthogonality condition is written as shown in this equation, which is the equation for delta function normalization we discussed earlier. This is the continuous spectrum analog of the discrete orthonormality relation as shown. So again, we see that the characteristic feature of a continuous spectrum, the quantical delta of the discrete case, is replaced by the Dirac delta. The corresponding coordinate representation is shown here. This means that different unbound states with E not equal to E prime are orthogonal, but only in the generalized or distributional sense. Since neither state is square normalizable, we do not interpret this as an ordinary inner product between two normalizable Hilbert space vectors. Rather, it is a delta normalization condition for generalized eigenfunctions. This distinction is important because students often try to apply the discrete spectrum normalization rules directly to continuous states. That doesn't work. Continuum states are not normalized to 1. Instead, they are normalized to a delta function. If the continuum states are labeled by momentum P or wave number K, instead of energy, the delta normalization takes the corresponding form shown here. So this slide is really reinforcing the mathematical message of the earlier continuum discussion. Unbound energy eigenstates behave like a continuous orthogonal basis, but only in the generalized sense. Now we arrive at the mixed spectrum completeness relation. At this point, it is very important to see the big picture. Bound states and unbound states are not just two unrelated categories. Many quantum systems contain both, having a discrete set of bound states and a continuum of unbound states. In such cases, neither the purely discrete completeness relation nor the purely continuous completeness relation is enough by itself. We must include both parts. So in bracket notation, the full completeness relation takes the form shown here. This means that the discrete bound states and the continuum of unbound states together form a complete generalized basis. The continuum integral should be written over the actual continuum range of energy. In coordinate representation, the same statement becomes this equation. So if we want to expand an arbitrary wave function psi, we must include both contributions as shown in this equation, with coefficients shown here. This is the natural generalization of everything we did earlier. For a purely discrete spectrum, we had only a sum. For a purely continuous spectrum, we had only an integral. for mixed spectra, we need both. As we mentioned earlier, the absolute square of C sub n gives the probability weight in the discrete bound state, while the absolute square of C of E times dE has the interpretation of the probability that the energy lies in the interval between capital E and capital E plus dE. This is the mathematically complete picture for many important systems, such as a finite potential well or short-range potentials in one dimension, where there are a few bound states and also a scattering continuum. So this final slide ties the whole discussion together. A physically relevant Hamiltonian may have both discrete and continuous parts in its spectrum, and the full state space must reflect both.